Yeah. Tom. Wait. Tom. Tom with a D. Yeah. Okay, let's get going. So the themes for the homework are posted. Hopefully you can see it. Also, there's a quiz coming up. I hope you notice that on the syllabus. It'll be due Sunday night. This involves watching a short video on specific yield and effective velocity, two important terms that take a look at that video and it gets you going, and then there are just a couple questions related to the videos. All right, so what we're doing now is trying to come up with a way to analyze the flow of groundwater. And the approach is to come up with a way first to determine the distribution of hydraulic head. Once we know that, we can take the gradient and use Darcy's law to get the flux. So we went through last time and we said that we could take this concept of mass conservation, and we figured that better apply, and also Darcy's law better apply. And so we took those two concepts, put them in mathematical form, and we came up with a form of the governing equation. And basically that equation embodies those two concepts. Okay, so we found this is what we came up with when we did it. Okay, and we've got on this side, we've got a derivative. That's the first derivative of a hydraulic head, hydraulic conductivity, and this says take the derivative of that. Okay, and there's recharge, and this is the hydraulic head changing with time. So this is the governing equation for a specific set of conditions. So it's one dimension because there's just one spatial dimension here. So it's just in the x direction. It's isotropic. That means that it's the conductivity is uniform. And actually, the way we have the conductivity here inside of this derivative, and they could be non-uniform, but it's, well, isotropic means that it's the same in all directions. So this is just one term, and so that means that it is indeed isotropic. Yeah, so it could be heterogeneous. That's the conductivity in here. There's recharge, and it's transient because the head can change with time. Okay, so these are all different components of or descriptors of this a version of the equation. So we can change it a little bit here, where so you see this term, it's there, and now we've added two more where we've got y and z. So instead of one dimension, this is now 3D. Okay, but everything else is the same. So it's still confined, it's still isotropic because these are all the same. And it's still transient because we have that term. It's still heterogeneous because the conductivities are inside of the derivative. and there's still recharge. Okay, so now, let's see if we can pull this down. I have subscripts here, X, Y, and Z. So that means that the conductivity, this is the conductivity in the X direction, and Y direction and Z direction. So that means that the conductivity has a direction. Remember when we did the layers of conductivity, or layers of, we had different layers, and we said that the equivalent conductivity for a uniform material was anisotropic. So when we get subscripts like that and the conductivity have a direction, then it's anisotropic. So this is now anisotropic, but everything else is the same because that's the only change we've made. And actually, all of these equations are in the handout, so you've got them. Okay, so now we're going to change it again. We're going to make it, we're going to switch it back to isotropic. And we're going to change the notation. So this is kind of cumbersome notation. It's kind of nice because you can see what's all going on, but often you'll see it written like this. So that thing there that's the gradient operator. And that says take the gradient of the hydraulic head. And this says take the gradient of that. Okay, so this stuff here, written out, you can write it in a more compact form. So sometimes you see it like this, maybe in the book, maybe it's written out like that. Okay, so these two are essentially saying the same thing, but different format. Okay, so if the hydraulic heads are not changing with time, then we have what we would call a steady state condition. So it could actually be that it's stable. It also could be like, we often will take a long-term average, and the heads are not changing with time on a long-term average. If the heads don't change with time, then this term right here, that's the time derivative, that's 0. Okay, so if it's steady state, this term here, it's 0. And if it's just 1D, we go back to this term here. So this is 1D steady state. And the hydraulic conductivity is still inside of this derivative. But if the hydraulic conductivity is uniform, then this is a constant. And remember, if we take a derivative of a constant, it just comes out. So the conductivity would come out, and you would have a derivative of the derivative, or the homogeneous case. Okay? So if it's homogeneous, this comes out, and then you have the derivative of the derivative, which is the second derivative. For that, it's been a while since calculus. Okay, so here now we have, of all of this stuff, the simplest form. This is 1D confined, isotropic, steady state, homogeneous with recharge. Okay, so we've got a bunch of different variations. We can solve these in different ways. The simpler ones we can solve with simple methods. This is probably the most complete right here. We can solve this with numerical methods. And so what we're going to do is take a look at a problem, and based on the conditions of the problem, that's going to tell us what kind of form of this equation we can use. If we only have things varying in one dimension, then we use the 1D case. We don't need the full 3D case. If it doesn't change in time, then we don't need this term. And so setting up the problem will be, one of the things that we'll do is take a look at what the hydrologic conditions are, and that'll allow us to determine the form of the equation that we need. Okay, so this, in the simplest form, we have this. And what this says is that the second derivative of the heads is proportional to the negative of the ratio between the recharge and the transmissivity. Okay, so what do you make of that? The second derivative of the heads in 1D is proportional to the negative of the recharge. We saw from Darcy's law that the flux is proportional to the gradient, right? So the gradient is like the slope. So the flux is proportional to the gradient from Darcy's law. So what is this saying? The second derivative of the head is proportional to the recharge. Well, it would be good to review the second derivative. The first derivative is the slope, and the second derivative is what kind of aspect of the what kind of aspect of the curve are we measuring with the second derivative? If it's a word problem, the first derivative is to the slope, as the second derivative is to the
Curvature, concavity.
curvature. Yeah. So this is how the slope changes. So if the slope is changing rapidly, then we have a large second derivative. So what about the sine? Plus, is that a plus second derivative or a minus? This side? Plus or minus?
Decreasing, it's negative. It's increasing, it's negative, right?
So if what's decreasing?
If the first derivative is decreasing, then the second derivative is negative.
If the first derivative, so this is the derivative of the derivative. It's like the change of the slope. So here, the slope is increasing, right? So the second derivative would be, yeah, and here it's negative, and here it's 0, right? Because the slope is not changing. Okay, so positive second derivative, negative, not changing. Okay, so this is the positive second derivative, and let's say this is a hydraulic head, in 1D, so this would be like a cross section of hydraulic head. So if this is positive, then what does that say about that term there? If this is positive, then in order to have this side be positive, you have to have one of these terms be negative, right? So look, the conductivity and the thickness, they can't be negative. So this means that the recharge must be negative. So we have this kind of a basin. We have, what it means is, the slope is going like this, flow is going like that, flow is going like that. There must be negative recharge or water being removed. Here, the curvature is negative. So that must mean, if this is negative, that must mean this is positive. And so this is like a groundwater ridge. This would be the groundwater divide, kind of the cross section that we've been drawing where there is recharge. Okay, so I think then, and then here, if the cross section of the hydraulic head looks like that, there's no recharge. It's just straight. The flow, the slope is the same everywhere, so the flow is basically constant or uniform, and there's no recharge. So the second derivative is 0, recharge is 0. Okay, so that's basically what that equation is saying. It says how the hydraulic head must be changing, what the curvature would be like based on this thing of recharge conductivity thickness. So one of the things that we'll see as we proceed with this is that in a lot of the examples, recharge and conductivity and actually, well, we'll also see for many of the problems, conductivity will be multiplied by B. So that's the transmissivity. And we'll also see that the transmissivity and the recharge enter as a ratio. So if that's the case, then if they only enter as a ratio, then the magnitude of one relative to the other is what really going to matter, not necessarily the individual magnitudes. Okay. So the problem that we looked at the beginning of the class last time was 1D. It was confined, isotropic, steady state, homogeneous with recharge. So this is the governing equation for that problem. This will ensure that conservation of mass is obeyed and the flow law is obeyed with Darcy's law is obeyed. But the other thing we said we wanted to do is have it be consistent with the field setting with that that conceptual model. So we need to include that. So for that, we're going to need to have some additional information. And here's our problem. And what we're trying to do is determine this curve here. That's the hydraulic head. And this thing here says how the heads have to behave in here. But the thing that's missing is what happens, what the hydraulic head does here and here. Okay, so in order to solve this problem, we have to include that information. And that will include as the boundary conditions for this problem. These are what the hydraulic head is doing at the boundaries of the problem. So we'll write the boundary condition as, you can think of it as another equation. So this is the equation. It says that the gradient in the head is equal to 0 at a particular location. So this is x equals 0. There's no flow here, so the gradient would be 0 where there's no flow. So that's the condition at that boundary. And then down at this boundary, we have another condition. The hydraulic head is equal to H1, which is the hydraulic head in the stream. And that applies at a specific location. Okay, so these two additional equations allow us to tailor the problem to this particular scenario, where we've got a groundwater divide here and a stream here. Okay, so that's going to make it consistent with the conceptual model of our field setting. Those are the boundary conditions. Okay, so that's the setup of the problem. Here's how we're going to go about. But here's kind of a step back, and this is the process that we're going through. So we had the field setting. We simplified the field setting, generating a conceptual model. Then based on that conceptual model, we were able to come up with a governing equation. It was 1D and steady state and so on. And then also based on the conceptual model, we had some boundary conditions. Okay, so that's a setup of this is kind of translating that conceptual model, which is a sketch, into a mathematical problem. Okay, then we need to solve this problem. So we need to solve the governing equation. And then we'll use the boundary conditions to complete the solution. Okay, so we're right here in this overall process. Okay. So here's the conceptual model. I simplified it a little bit. We've got recharge coming in uniformly, boundary condition here at x equals 0, and boundary condition like that at x equals L. So that's step one. Step two, the governing equation. And then we got to go and do the solution. Okay, so we have to solve this. This is a differential equation, and we solve it. In this case, we can solve it in a simple way just by integrating. So we integrate both sides. We integrate both sides of this. We integrate the left side, we get first derivative, and if we integrate that, it's just a constant. So get that plus a constant. Well, sorry. Get an X in there. Okay, so we start with this, integrate it once, and we get that term, and then a constant C1. And now that's the gradient, that gradient, we're gonna integrate it again. And we integrate that, we just get H. And if we integrate this, we get R AB X 2. And we integrate that, we get X, C1X. Okay, so that's essentially solving this equation for the head. We just do it by integration. So if we wanted then to plot this up, that's what we want to do, right? We saw that yellow curve on the previous slide. We see that there's going to be a problem. That we could plot that. Presumably we have this, from our field setting, but these two things are going to cause a problem. These are constants that come from the integration. So they're popping out from the mathematical procedure that we did to the integration, and we need to deal with that. But when we set the problem up, we had these two boundary conditions. Those are additional equations. So we have these two unknowns. We've got two more equations. So we can use those boundary conditions, those simple equations from the boundary condition to solve for the constant. So do that here. We'll have a little bit more room. So there's the equation after we've integrated it. And that's what I have here. Yeah. So there's one boundary condition, and there's the other boundary. So the way we're going to do it is this is really like two equations. So this says what the gradient can be at that location, and this says what the head is at that location. So the way I usually would do this is start with the boundary condition at x equals 0 first. That's the easiest one. And if we look back on the previous page when we integrated it first, we got that first step, we got that, right? So this boundary condition says that dh dx is equal to 0 at x equals 0. So here's dh dx. We just say that this dh dx is gonna equal 0 when x equals 0. So we substitute in x equals 0, that's just gonna make that 0. And then we get C1. So C1 plus 0 equals 0. So it looks like in this case C1 equals 0. Okay, so that's kind of nice. Get rid of that one. We just don't have to deal with C1. All right. So we'll do the same procedure here. We're going to take the equation for heads and we'll substitute in h is equal to h1. So that's going to become h1. And then where we have x, we'll substitute in now. So this will become that's h1, and it's minus r over 2kb, and then x, that's L squared, right? Because we put substitute in L there. And now we have C1 times L, but we already know that C1 is 0, so we don't have to deal with that. So we can ignore that because then C1 is 0, and then we have C2. Okay, so we have to solve for C2. Looks like we just bring this over here. So C2 would be H1. We add that to both sides. Okay, so that's the constant. And now we substitute back in here. So say H plus C1, which is 0, and then plus C2, which is H1. Okay, so that's what the hydraulic head looks like. So we have a feel for what that would look like plotting it up. I mean, we could go and assume some values here. But you have a feel for what that would look like. We did plot it up. So do an air graph, right? Do an air graph. So if air graph is linear, that's like a straight line, or increasing slope, decreasing, wavy. What do you think?
Upside down parabola.
Yeah, so upside down parabola. So there, this is all constant. So this is going to move curve up and down. That is the parabola. So this right here looks like this. If we change the sign, it goes like that. This amplifies it, but it still would just be this. This term here looks like that. And then this term here brings it up like that. So it lifts it like that. Okay? So the part that we're interested in is right here. Okay. And it's going to go from there down to some value here, x1. And when we drew in our little sketch, that's kind of what we drew, right? And it has a bit of curvature. It's sloping in that direction. The flow is going in that direction, and it has some curvature to it. Okay, so it seems like this is on track. One of the things that we might want to do, and really one of the benefits of working out problems like this in mathematical form, is that you can get some insights into what's controlling the hydraulic heads, and then also maybe some ways to utilize that. So one of the things we could do is we could say, well, right here at the divide, that's where the hydraulic head is the max. So we could say, what's the maximum hydraulic head in this situation? Well, H max occurs where x equals 0, right? So at x equals 0, that's 0. And we just have this. So H max is and we could say, we could subtract this off of both sides and just say, well, okay, if this thing right here is going to be how much the difference in the head between the head here at the divide and the head here at the stream. So how much does the head change from the stream to the divide? And it's this. Okay, well, I mean, that's kind of cool. This is something we could measure. We could go out and we have a well at the divide. We have a stream, the difference between the water levels, that's this. So we could measure this independently. And then if we knew the transmissivity, this is just the distance from the divide to the stream. So we would know that. So if we knew the transmissivity, we could measure that and estimate the recharge. So that would be kind of cool. Be an easy way to get an estimate of the recharge. We can also take a look at just this grouping of variables. Okay, try to get some insights into that. So one of the things we see is that the recharge and the conductivity, or the recharge and the transmissivity, enter as a ratio. Remember, we saw that we saw that in that previous example. Here it still is the case. So what that means is that the control on the hydraulic, on the maximum head here at the divide, depends on both these, but it really depends on the ratio. So if we increase the recharge, we'll raise the head of the divide. But if we decrease the transmissivity, we'll also do the same thing. If we increase this by twice, we raise that by twice. If we cut this in by 1/2, then we also raise that by twice. So I mean, I think that makes, I mean, the recharge, if you have, if you've got this kind of a thing where the recharge is coming in, here's the stream, then I think it makes sense that if you double the recharge, you're going to increase the head, right? But it's not so clear about the transmissivity. But I think you can see that because if the transmissivity is reduced, but the recharge stays the same, then the flow is the same. And if the flow stays the same, but the conductivity is decreased, then we have to have a steeper hydraulic gradient to get the water to flow out at the same rate. Okay, so if we cut the conductivity, we have to have just the steeper gradient here, and that ends up giving us this higher head. Okay, so there's some insights about how recharge and conductivity can interplay between them. We also see that the maximum head, it depends on this L squared. So it has a strong dependence on this, and this is something that's easy to measure too. This is the distance from the stream to the divide. So if we have a watershed like this, and do a cross section, and if these streams are at roughly the same elevation, then, and everything is uniform, the divide will be roughly in between. And the head depends on that distance squared. So where the streams are further apart, if you separate the streams by a factor of 2, you increase this head by a factor of 4. Okay, so that gives us some insights about what to expect the hydraulic head here at the divide, how it would depend on the spacing between the streams. Okay, so that's, I don't know, some nice insight that we can get from just this simple analysis. Okay, well, good. Let's. Okay. Oh, so we're also asking about the flux. So we want to predict what the flux is here in this model. We've predicted what the heads are here. So the flux, what do you think? What's the strategy for getting a equation for the flux? So remember from Darcy, and that, and you know what this is now? It's C1 is 0. So that's the head gradient. So we can just say that the flux is this minus K times that stuff. The minus makes that a plus. And I'll just write that out. So R over KB. So the K's cancel. Oh, and X. So the flux is equal to R over B times X. So that's just this. Flux as a function of distance looks like that. So pretty simple. The flux at the divide is 0. Makes sense. And it increases linearly. And it doesn't depend on the hydraulic conductivity at all. So that's, I don't know. I mean, I think if you think about it, that makes sense because you have the recharge coming in, and as you move along in this direction, you have more and more recharge accumulating, and that's why the flux is increasing. And if it's just accumulating recharge, then the flux doesn't really depend on the conductivity. So I think that makes sense. But because I usually think of flux in terms of Darcy's law and conductivity being there, this was a little surprising. But that's what falls out of this analysis. So we can go through and do this analysis and predict what the head distribution is, learn about the maximum head, and then also the flux. Okay, so I think that's pretty good extraction of some insights from this simple analysis. So what I'd like to do is try that again and do another example, and also take us a bit of a step back and look at this step where we go and get a conceptual model and then translate that conceptual model into an analysis that we can solve. So one of the things we'll have to do is determine the form of the equation from hydrologic conditions and the boundary condition. And then we'll solve for the heads and use the boundary conditions. And then what I want to do for this example is estimate the location of the divide. So what we did before with that first example was we just assumed where the divides, assume we knew it. But then we don't know it. And this one, with this example, will determine where it is. It will also determine what controls the location of the line. So here's the problem. So we have two streams here, and recharge uniformly distributed, and flow goes to one stream, this flow goes to the other stream. And in this case, we're going to have the streams be at different elevations. And that'll cause some interesting effects. Okay, so here's the approach. This is what we saw last time. Same approach. We're going to have the conceptual model, get the form of the equation, boundary conditions, and then solve it. So when I show you that slide with all those different equations on it, these are the different things that we were considering: dimension, time, structure. This would be dimensions like 1D, 2D, 3D. Time, is it transient? Yeah. So transient, steady. Structure, is it homogeneous or heterogeneous? The fine structure, that's this fine layering. And this would be whether it's isotropic or anisotropic. And then sources or sinks, recharge would be a type of source or wells. And then aquifer types, this is confined and unconfined. So we're gonna come up with those different aspects. The other thing that we need to do is determine the boundary conditions. So in that example that we just saw, there were two types of conditions. Basically, the way that it's going to work is for boundary conditions, they're going to be, we're going to specify something about the variable that we're solving for, the dependent variable. So that's the hydraulic head. The boundary conditions will be specifying something about the hydraulic head, either what the hydraulic head is, or what the derivative, what the gradient of the hydraulic head is. The gradient is proportional to the flux, so that when we specify the gradient, we also think about it as specifying the flux. So those are the two main types of boundary conditions. Type 1, we specify H. Type 2, we specify the gradient or the flux. Now we saw that 1D problem. The way we did it was we integrated, we got a second derivative, we integrated it twice. Each time we integrated it, we got a constant, and we needed a boundary condition for each one of those constants. Okay, so if we have 1D problem, we need two boundary conditions. If it's a 2D problem, then it's like this. And if it's 1D, we need a condition here and a condition here. If it's 2D, we need a condition here and here and here and here. Okay, and if it's 2D, we've got a second derivative in X and a second derivative in Y. So we think about integrating both of those, and we need then 4 constants, and for 3D, we would need 6. Okay, so we can have those conditions, and we can have these different types. All right, so here's what happens when you specify these boundary conditions. So we can, the type 1, we specify the hydraulic head. So if this is the problem from 0 to X something, this is a boundary. And if we specify the head, then we say that the head has to be this here. That's what we mean by the boundary condition. So here's what can happen. the head could be like that. Right, that's kind of what we saw in that example. It could be like that. It could be like that. Okay, so it could do a lot of things here in the problem domain. But when we get to the boundary, it's got to be there. Okay. So that's this type 2 specified head at the boundary. For type 1. Type 2 boundary, we specify the flux at the boundary or the gradient. So what we're saying is that the gradient has to be that. Okay? And if we're specifying the gradient, then we're just specifying what the slope is, but we're not actually specifying what the value of the head is. So, yeah. So here, through Darcy's law, the flux and the gradient are proportional. So if we're specifying the gradient, then it could be like that, or like that, or like that. Right? So it could, in here, it could be anything. But once we get to the boundary, it has to have this gradient, but we don't know what the actual value is going to be. Here, we know what the actual value is going to be, but we don't know what the flux is going to be, or what the gradient is going to be here at the boundary. It could be anything. Okay. So there'll be a common type of boundary condition, type 2 boundary, where the flux is equal to 0. We used that one in the first example where we had a divide. And in that case, what we're saying is that the slope here of the hydraulic head is equal to 0. And so there's no flow here, but the head out here could be, could vary like this. So we need to be able to go from our conceptual model where we describe the hydrogeologic conditions and come up with these boundary conditions. These are the options that we have. So if we have a conceptual model that looks like this, here's surface water, and here's the aquifer that we're going to be interested in analyzing. What we're going to assume is that the surface water is controlling the hydraulic head in the aquifer here, and the hydraulic head in the surface water is H1. And so we assume that the hydraulic head right here in the aquifer is equal to that of the surface water. And so one way to analyze this is to basically chop off the model domain and say that at that point, we're going to specify the hydraulic head, and that's a boundary condition. So surface water is represented in many cases as a specified head boundary. Groundwater divide, so right here, the flow is 0. So we could represent that as a no flow condition. Another scenario that's fairly common is where we have a big contrast in hydraulic connectivity, going from a sand to a clay, for example. In which case, the low hydraulic conductivity of the clay would mean that the flow in the clay is small, typically, compared to the sand. So what we might say is that we're just going to ignore that small flow in the clay and make a boundary right there and say that we're not even going to include that. We're just going to assume there's no flow and have a boundary condition. Okay, so those are some examples of hydrogeologic conditions that we can represent as boundary conditions. Here's another condition where we have a well. And if we have a well, then we've got flow going to this well. We know what the volumetric rate coming out of the well is, right? Because we can measure that. That equals the flux right here at the well times the cross-sectional area. So we can take the cross-sectional area over there, and the flux is equal to the flow coming out of the well divided by the cross-sectional area. So the cross-sectional area is like this cross-sectional area, that the surface area of the well, which is the circumference, pi times d, times the thickness here. So that's the flux. We can also then set that equal to Darcy's law. So this stuff that we would know, the pumping rate, the well diameter, the length here, we set that equal to Darcy's law. Bring the conductivity over here, and that gives us the gradient of the hydraulic head here at the well. Okay, so the gradient is equal to this stuff. Things that we would know, the conductivity, we set the model up with the flow rate of the well, the conductivity of the aquifer, these dimensions. Okay, so this is a bit more complicated. We've got these terms here, but this is an example of this type 2 boundary that depends on, or that is the gradient being specified based on some conditions for the model. Okay, so that's another kind of boundary condition. And now we're ready to go into the overall conceptual model, specify the boundary conditions, and then solve it. And that'll be a good place to pick it up on Monday.
Yeah, never do. You read it about?
Yeah.
Stuff away.